There's no one yet, no? No one yet. 3. Yes, good afternoon, everyone. So this is again a live session, the second live session organized for this advanced quantum mechanics field applications. We had one earlier. Please ask your questions. Uh, Rahul, I have received this complaint earlier. I do not have a solution because this was earlier, this problem didn't occur. Um, uh, Let me talk to the people concerned, and if we can delay the submission, um, that will be helpful for you. Um, 7th week's assignment is given. All right, I will. I'll sort of look into this. I'll speak to the NPTEL people. Assignment number 3, it'll be corrected. They'll do it. They'll do it. They already have done it. Might not have posted the marks. Aman, good evening. Week number 3 and 5. They have all been corrected so far I know. The TAs have worked on that, and they might not have posted the marks which I'll ask them to provide. Oh, you mean to say the assignment actually preceded the week's lectures? All right, this is new to me. I don't know why it has happened because it hasn't happened earlier. More importantly, please use this time to ask for your conceptual questions, more like the the problems or wherever you have found things to be conceptually difficult or you haven't understood. So please use this time. But of course, the other things are important, I understand. I'll ask the TAs to communicate with the NPTEL office in order to see if anything can be done. Question 2 of assignment 6 is a little confusing because we are asked to calculate the first and second order Stark effect using variational principle. Why is that confusing? For variational principle, you have to write down a variational wave function. So you speculate that wave function and calculate the first and second order Stark effect. That should not be confusing. You just have to guess a variational wave function for the hydrogen atom. I believe it's in the ground state. So the hydrogen and the electron is in the ground state of the hydrogen atom, and then so it's actually 1 by root over pi a naught cube and exponential minus r by a0. So suppose you don't know this and you simply write a exponential minus r over alpha and then do a first order expansion or first order correction and even a second order. Second order is just that you need an intermediate state for the second order Stark effect to calculate, so you need a first excited state as well. That is what the question is probably. So I believe the solution of the assignments have been posted by the TAs. I've asked them today. They said yes. Sundar, what potential Z direction of EF plus R, in which context are you asking? And what is EF? Electric field, you mean to say? No. If it's in answer to Aman's question, then the unperturbed states correspond to 1 over R potential, which is coming from the hydrogen atom. And then on top of that, you add the electric field in the Z direction. Rahul, good question. Perturbation may increase the true energy or it may decrease. We have seen examples in which in some cases when the states are degenerate, they could increase energy or decrease energy. Sometimes they do it symmetrically or they may not do anything to certain states. It depends upon the selection rule, it depends upon the form of the wave function. And so on, because say a S wave state doesn't get affected by this potential, which is like Z, which is R cos theta. So it is not, there is no rule that whether it will increase or decrease, it can do both. Wave function is given in the question, but my question, what is the meaning of order? Oh, order means it's the order of E, the electric field. So if you calculate the correction to first order in the electric field, then it's a first order perturbation theory, or using variational this thing. And if it's second order in E, that is E square, then it is second order. Yes, Sundar Ramchandran, Stark effect plus variational principle. So you know the exact eigenfunction. Oh, for the variational, yes, you take the exponential minus R by alpha and then you use the electric field in the Z direction. Okay. Yeah, I understand your question. Yes. See, perturbation theory and other, this approximate techniques such as variational theory or WKB approximation, etc. They are not exact solutions, but then you cannot solve the problem exactly. So you need to resort to some approximations, and these are some of the approximations which are controlled. Because you need to understand that if you do an approximation and if the approximation is not good for that particular problem, then the answer that you get is not too much of is not of any meaning. But perturbation theory is only valid when you have the perturbation term to have which is something like 1 by 137, which is alpha times the alpha is called as the fine structure constant, which has a value 1 by 137 of the unperturbed energies, which we have written throughout by H0. Okay, and all these things. However, variational can be when the potential term is either weak or strong. WKB is for a very specific kind of potential. It's a linear potential. In case of spin half particle, though the eigenvalue for a component of plus minus half, do the amplitude determine the resultant spin direction? No. You see, the spin half particle, the resultant spin direction is not determined by the amplitude. Okay, so this is when you say that the eigenvalues are plus and minus half. What you mean is that you have written down the spin half particle in the basis of the z component of spin. All right. So when you do it in the basis of z component of spin, you get a plus minus half, and then you solve the problem. You find the eigenvalues and the eigenvectors. The eigenvalues are exactly what you said, plus and minus half, and there be eigenfunctions which will have some amplitudes, but they do not correspond to the resultant spin direction. No. You can write down all these spin matrices, either spin half or spin 1, in any basis. That is, either it can be x, y, or z, or even pointing in an arbitrary direction, which is n cap. Spin x, spin y, spin z resultant. No. So if you are asking that whether plus minus half is the z component of the spin, so these eigenvalues for any of the component, yes, it is. In fact, it is plus or minus 1, not half. In fact. So all these things are plus and minus 1, and their eigenfunctions are different. Just that. So if you're talking about the amplitude of the eigenfunction, then they do not talk about a resultant spin direction. No. We should connect it out. So these are So these are, so these are sigma x is equal to 0, 1, 1, 0, sigma this x. So sigma y is equal to 0 minus I 0. Sigma z equal to 1, 0, 0, minus 1. So if you diagonalize them, you get a plus minus 1, and then things have different eigenfunctions, and so eigenfunctions, if you normalize, they'll have different eigenvalues, but this plus and minus one, they do not talk about any specific direction. So these are spin half, and the same thing holds for spin 1. But the only thing that you should remember is that when you write a matrix, you need a basis. So the basis here for any of them is like, so I'm writing it with a conjugate of this and this. All right. This you should understand that this is actually the sigma z basis. So we write everything in sigma z basis such that sigma z is diagonal, but sigma x and sigma y are off diagonal. So that's the so this this sigma sorry, not sigma. All right. So this one. So this is your up, and then sigma x is equal to 0, and so on and so forth. So that's what I mean by the basis. Let's go. Let's see. Okay. Yeah. Can we make measurement of an entangled state to know about the state hypothetically in another universe? No. Rahul, so the entangled state cannot be disentangled. But that is crucially needed for teleportation. So that is not, you can't separate out if you mean by measurement, if you mean separating out the entangled state, then you cannot do that. Sundar, I guess angular momentum would have resultant. Yes, angular momentum and spin angular momentum, they are similar vectors. They both have classical and quantum analog. They both rotate in the same way in both classical mechanics and quantum mechanics. In quantum mechanics, we talk about commutator bracket. So the components do not commute. That is Lx, Ly do not commute to give you 0, or Ly, Lz do not commute to give you 0. Same holds in classical mechanics for the Poisson's bracket. Assignment third is removed. Will question not come in that section? No, that I cannot tell you. If I don't know why it's removed, but I'll ask the TAs. So if you remember to ask me that question, I will ask the TAs that if it is, why is it removed, and so on. You have to do thoroughly all the tutorials, that is all the assignments you have to do thoroughly and understand all these things such as entangled state and how does one make measurement and what happens when you apply a sigma x operator and so on and so forth, perturbation theory, first order, even sometimes second order for a trivial perturbation. Okay, so second order is a little slightly more tricky, but I have shown that how to do this. So this is Stark effect, Zeeman effect, or some potential in the particle in a box. Those kind of things will come, and something from basics as well. I mean, in the sense that these early quantum theory will also be there, where we have talked about how all these photoelectric effect and all that Compton effect, etc. So all those things will also be there. So please prepare the tutorials properly, follow the class notes. I mean, notes means the class videos rather. Thank you. This is exactly the same question that has been asked, because so what it means is that you write down the variational wave function, and so this is a little tricky, because you have to make a when I talk about the second order. This means that you have to also write down the variational state for the first excited state of the hydrogen atom. This is why you're not getting it. Okay. So first order I think is clear, but the second order is a little tricky. That's why the problem is not so straightforward. Wait for the TS to post the solution. You'll see that what I've done is I'll write down the solution for a variational wave function for the first excited state, and that's what you have to do. Here you cannot use the usual second order expression to get the correction. So this is a difficult thing, slightly difficult. Probably if you look at this book called Schiff, L.I. Schiff, it's an old book. I don't know whether still is there in print. You can have a look at it, and probably even some e-copies could be available. I don't know. You can see that in order to understand what is there. But otherwise, I'll ask the TS to post the solution. Even in the ground state, if we introduce cos theta term in the wave function, I guess we have to introduce Laplacian for theta 2. Are you saying this in the context of this first order, second order? Then you don't have to do Laplacian, because you simply have to calculate the expectation value of energy with respect to the variational state. So the Laplacian is not required. But if you're normally talking about hydrogen atom, then you need to use Laplacian for the theta and phi both. Yeah, that's right. Yes, of course. Oh, you mean to say that? Yes, yes, yes. To calculate the total energy. Yes, 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 yes. You're correct. No, Sundar, you are correct. Absolutely correct. There you need the Laplacian. Yes, right. I was just more thinking of this, the Stark effect term. Yes, you have the kinetic energy, and the kinetic energy involves Laplacian. Yes. Phi term, yes, you can neglect because I mean you should not neglect that phi term. The phi term would be there, but that part would eventually give you one because you have that is normalized. So if you want without the phi term, that's fine because the other term, which is the Stark effect term, doesn't have phi. It has only theta and r. So it's Z, which is r and cos theta. Yes, you're correct. That's right. This is a very specialized question, 1 by r to the power n. You will find it in some books they have done. I don't think you get it as so 2s is L equal to 0 and so on. So you calculate. So you have to take a 0 to infinity and then 2s state and then 1 by r cube. It should not come as infinity. Yes, you're correct, Sundar. Yes, in perturbation you ignore the Laplacian means because you already have taken into account the Laplacian while calculating the unperturbed states. But in variational, you have to take the full Hamiltonian. You are absolutely correct. That's right. What do you understand by reference tables? Some integral. If it's some integrals or some result of some integration, that will be given. Aman, I have to see because 1 over r cube is not a very normal thing to do because your potential goes as 1 over r and your so 1 over r cube is like a perturbation. So your 2s term probably has some r into some, it's a basically the log-wire polynomial multiplied by r exponential minus r by a0. The first, I mean L1, and then you have 1 by r cube, and then you again have that r, and then you have r squared dr. I think it will be because of the exponential. It should not give you diverging term. Oh, yes. All those things will be given. Yes. Sundar. Spherical harmonics, hydrogen atom. You don't have to remember them. They'll all be coming with the question paper. But still, I would suggest that please keep all these, at least y00 is like 1 by root over 4 pi. And say Hermite polynomial, first one is constant, the second one depends on x, the third one depends on x square. Some of these lower ones you should keep in mind. Where can we get tutorial videos? I don't know. Tutorial videos are not there. I mean, there's nothing called a tutorial video. The tutorial solutions are all posted to you. Values of constants will definitely be given. Yes, it just comes with a question. You don't have to even go to the front of the question paper or the beginning of the question paper. It will all come with a question. Aman, I'll have to see this. Okay, 1 by r cube expectation should not blow up, but you are saying for the 2s term, I will see that and I will reply back to you. I have your email. So why I'm saying that it should not is because you have a r square in the integral, and there's a 1 over r cube, but then the 2s state also has some r contribution. So that should kill, and you get a gamma function integral. But I'll have to see this. Sundar, your question is very valid. So, in the limiting case, if you localize the particle to a position which is, with a desired accuracy, then you actually make the momentum uncertainty become infinite. Such situations are, they do not arise in real systems. So, because of the finite wavelength of the particles, the particle always has a uncertainty in position, which is not. So there's a delta x there. So delta p is also finite. So such things do not arise, but yes, if you try to do it, then the momentum uncertainty will go to infinite. Delta P will go to infinite. Yeah, so what about squeeze states? They are very special. You're correct that these squeeze states are very special, and they have applications in optics. Yes. Aman, alpha is a variational parameter. You should not assume alpha to be smaller than 1. Then, of course, you're not doing justice to the variational wave function. Okay, so your alpha is simply a parameter, it can be anything. Yes, Sundar, I agree with you. Yes, for squeeze states, that's what happens. In a variational, you're not allowed to do that. I am failing to understand what is alpha divided by plus alpha whole cube, which is 1 over alpha square. That's what you mean. No, you cannot take in a variational thing, you cannot take that to be a small quantity anyway. Yes, absolutely. Yes, you don't have to, Sundar, you don't have to do that. They're already normalized. Yes, you don't have to use the mods. I mean, psi square average. I mean, psi square integral dv equal to 1. They're already normalized. Alpha plus 1 plus alpha whole cube. Alpha divided by 1 plus alpha whole cube. Uh, no. You should not do that. Aman, you should not do that. Please post the questions. It's only about 15 minutes left. Time reversal operator. See, the point is the time reversal operator, there's nothing called time reversal. So it's basically the particle going in the opposite direction. That is what is called as time reversal. And then there are some symmetries, symmetries such as, um, something like translational symmetry. So if you are translating a system by some vector, and if the physics remains invariant, then you call it a translational symmetry. And if that happens, then there's some quantity that remains invariant, some physical quantity that remains invariant and would denote the constant of motion. So in this case, the constant of motion is the momentum. All right. And then for time, if the Hamiltonian does not explicitly depend on time, then energy is a conserved quantity. Say for example, if there is a rotational invariance, that is, it doesn't matter whether if you rotate the system by 2 pi or pi by 2, the physics of the system remains invariant. So then it is called a rotationally invariant system, in which case the angular momentum remains conserved, which means that LH commutated equal to 0, or dl dt also vanishes. So dl dt equal to 0, which means torque is equal to 0, and things like that. So these are the points about symmetry. So when the system has certain symmetries, that means that some physical quantity remains conserved, and then you can write down the common eigenfunction. So you don't need to solve the Hamiltonian. Maybe you have already solved the other physical problem, and that's how you say that. So that's how what we did. If you remember, for the hydrogen atom problem, we did not solve the theta phi part, because apart from a constant, the theta phi part of the hydrogen atom Hamiltonian is exactly same as the angular momentum operator. Okay, L square, rather square of the angular momentum operator, whose these things are like YLM functions, which are spherical harmonics. When time reversal operator commutes with the Hamiltonian, that means energy is a constant of motion. Time reversal operator is slightly tricky, because it is an anti-unitary operator. So it's not a unitary operator because of a complex conjugation term, but it means that the energy is conserved. All right. Thank you. Unfortunately, Aman, this is the last session because it's an 8 week course, and it's there are two sessions, two such live sessions. But you can post your queries to me or in that portal. That also will get answered. Yes, we can do that, Aman. Before that, you post all your questions, we can have a meet. All right, it's about, yeah, thank you, Aman. Thanks everyone for watching. And if you have further questions, of course, you can ask me or do it on the portal. You can ask on the portal. I shall reply. Not much, but there are, of course, it's a difficult course, as it says, it's an advanced quantum mechanics. So there'll be some advanced level questions as well, but there'll be some easier questions for you to attempt and solve completely, fully, okay, so that you do well in the final exam, right? I believe there are no more questions, so we'll hang up now. Thank you very much for your attention and watching this live session. All the best for your exams, final exam.